Hello, everyone. Today, I would like to talk about one of the recent discoveries we have made in our group. Um, I will direct you to the paper, but right now, most of the existing leaderless or leader follower algorithms, you can name it consensus, synchronization, containment, so on and so forth, are based on a very specific Laplacian null space. So, let's see what we can do more with multi-agent systems. For this, we first need to review what we have discussed about Laplacian null space directly or indirectly during the last couple of lectures. Uh, I will look at the leaderless setting, leaderless case. We have this consensus algorithm, and in this lecture, I will focus on undirected and connected graphs. All right, so for undirected and connected graphs, if you define aggregated state vector as x1 to xn, you can write this consensus dynamics into x dot equals to minus lx form. How you obtain L is the degree matrix of the graph minus the adjacency matrix. We discussed this. So, little example, let's say we have three agents over these undirected and connected graphs. Degree matrix for these agents, this has one neighbor, two. Two has two neighbors, and three has one neighbor, so 1, 2, and 1, diagonal matrix. And adjacencies of diagonal matrix determining which agent collaborates with whom. Agent 1 exchanges information with Agent 2. That's why we have 1 here. Agent 2, on the other hand, exchanges information with 1 and 3. That's why we have 1 and 1 here. Last one, 3 exchanges information with 2. All right, B minus A will give you this Laplacian matrix for this graph. All right, so what I'm going to say is not, of course, limited to this graph. It is basically for any undirected and connected graph, the Laplacian matrix that you are going to obtain will be symmetric. First of all, that's the first property, right? L becomes L transpose. And the second important property, the first eigenvalue of this graph, Laplacian, is 0, and all the other eigenvalues are positive since it is connected. And this 0 eigenvalue, we reviewed this, it corresponds to the eigenvector of ones. This is like 1, 1, 1, a bunch of ones. And this is because it comes from the null space property. Null space of this Laplacian spans the vector of ones. You can directly satisfy this equation, right? If you have a matrix and if you are multiplying by some vector, if it produces the 0, 0, 0 vector, then this belongs to its null space. And in this case, you only have one zero eigenvalue and you only have one null space vector, which is once. Now, all right, so I should mention this. I discussed briefly at the beginning, but almost all multi-agent control papers adopts such a Laplacian, and that Laplacian have the same null space of vectors of ones, 1, 1, 1, 1. That's why once you implement this algorithm, everybody converges to each other because when your null space is 1, 1, 1, 1, 1, everybody equals to each other. I did this in one of my previous lectures. I am now trying to find, I don't want to go back and forth between algorithms because I respect your eyes, sorry for going back and forth. I am trying to, okay, this specific figure. All right. This was from the introduction. This is the second video of the playlist on lectures on multi-agent systems. I was discussing some consensus versus synchronization at a very high level for two-agent systems. But here is the null space. It corresponds to the vector of 1, 1. This is the consensus algorithm for two-agent case. And as you see, depending on where you start, your initial conditions, you converge to the null space and stay there. And it's a form of semi-stability. We discussed this. This is in the second video. I don't want to go back and forth, but I want you to remember this figure. They converge to this 1, 1 null space. And this is no different once you have n agents. You have, instead of converging to 1, 1, you are going to converge to an hyperplane, which is like x1 equals to x2, x2 equals to all the way up to xn. So you converge to 1, 1, 1, 1. And since most of the results on multi-agent systems corresponds such a Laplacian having the same null space, they really scratch the surface of the research, deep research, what kind of deep research we can do. So think about like this, instead of having just this fixed null space, 1, 1, 1, 1, if we can assign whatever we want to our null space, then then we can tackle much broader problems in multi-agent systems, and we can generalize all this consensus synchronization, containment, so on and so forth. And this brings us to this paper. Throughout my career, I authored many papers that I don't remember the numbers right now, probably 300, 400. Maybe I'm right, maybe I'm wrong. But this paper is one of the papers that I really enjoyed while developing it with my students. So this is called basically how we can assign and distributively control Laplacian null space in multi-agent algorithms. So let me dive into the material directly. I'm going to call it new Laplacian. That's what we call in that paper the new Laplacian matrix. All right, new Laplacian matrix x dot equals to minus L bar. So this L bar will denote the new Laplacian matrix. I will put bar, all the new stuff. And if I don't put any bar like this adjacency, this becomes the regular adjacency that appears in the standard Laplacian matrix. What I mean by standard, this is the standard Laplacian matrix DNA. When we have this new Laplacian, all I'm saying, A doesn't change. We are changing D. So I'm going to call it D bar. What is D bar? Diagonal AW, inverse of diagonal of W. What is this W? W is the desired null space. Bear with me for a couple minutes. You will get the most out of this lecture. uh, you will understand. So this is the desired null space. So W, instead of 1, 1, 1, 1, it can be anything, 1, 2, 3, 5, 10. For example, to get a feeling of this new Laplacian matrix, for example, right, if you would like to assign a vector to the null space, so you need to satisfy this equation, L bar multiplied by W needs to be 0, 0, 0 for this particular graph. Why? Because that's the definition of the null space. You have some matrix. If you multiply it with a vector that is on the null space, then you are going to get 0, 0, 0, 0. I am doing exactly the same thing here. Basically, for this L bar, for this W to be in the null space of L bar, you need to get 0, 0, 0. So I'm doing this multiplication. So I have this D bar to be determined right now, minus the standard adjacency matrix. I just put it here, A. And D bar is D1 bar, D2 bar, and D3 bar. It's a diagonal matrix. If you sum them up, or subtract from each other, you have this matrix multiplied by W. What is this 1, 2, 3? I choose W to be 1, 2, 3. Why not? This is the null space. If you don't like it, you can do this exercise for example, 5, 1, and 3, or 5, 2, 2. Why not? So you can assign any vector. I am choosing W to be 1, 2, 3. For the sake of this example, it needs to be 0, 0, 0. So I have 3 equations and 3 unknowns. Basically, if you solve these equations, you are going to get D1 bar to be 2, D2 bar to be 2, and D3 bar to be 2 over 3. So now You can do this by hand, so you can choose D bar, D1 bar, D2 bar, and D3 bar to satisfy those equations. Then basically you are assigning this W123 to the null space of this new Laplacian matrix L bar. Yay. All right, so what this equation does, or how we crafted this equation, is basically instead of doing this by hand like this, you have this W vector. If you choose D bar to be like this, and if you perform new Laplacian L bar to be D bar minus A, then this W becomes the null space vector of this new Laplacian matrix. So this does it automatically. Either you can solve by hand, or if you can type this equation, you are going to get 2 over 3, which matches the solution that we have from these three equations. Once again, L bar, this W to be null space of L bar, this needs to be 0. And doing this exercise, you are going to have three equations. And if you solve these three equations with three unknowns, you are going to get D bar by hand. If you do it automatically, use this equation that will assign W to the null space of L bar. All right, I think you got the idea. So I would like to disclose properties of the new Laplacian matrix. First of all, we are not changing the adjacency D bar, which is the diagonal matrix. It changes, so it is symmetric. It remains symmetric for directed, for undirected and connected graphs. So L equals to L transpose, L bar equals to L bar transpose. And theorem 2.2 of our paper says that still like the standard Laplacian matrix, my bad here. The first eigenvalue of this new Laplacian matrix is 0, and all the remaining eigenvalues, second to last eigenvalues, becomes positive for this, new Laplacian having any desired null space. And basically, you can satisfy this, not in the context of this example, but generally, you can say that the zero eigenvalues eigenvector corresponds to W, which is on the null space of L bar. You can really show this. We did it here, but L bar multiplied by W becomes 0 if you use this equation. First of all, L bar W is this D bar multiplied by W minus A multiplied by W. Basically, I multiplied L bar with W, or D bar W minus A W. So this gives you vector of ones, if you think about it, a diagonal matrix inverse multiplied by the vector corresponding to diagonals. So this multiplied by ones gives AW. So AW minus AW is 0, and hence W is indeed the null space of this new Laplacian matrix L bar, which corresponds to the eigenvector of the zero eigenvalue. You can still go to the second eigenvalue. It acts like the Fiedler eigenvalue. You can look at the second eigenvalue close to the imaginary axis, its real part, and it will be real since this matrix is symmetric, so you can understand how fast it will converge. Let me highlight a result, then I will do one numerical example, then move from leaderless case, consensus-like case, to synchronization type of leader-follower case. This is the algorithm when you implement agent-wise. If you take this x that equals to minus L bar x, if you write it agent-wise, you have the summation. J is my neighbors. So Vj over Vi. And this Vj over Vi, it is coming from the elements of W. It can be defined before any mission. Or they can be also generated in real time, but I don't want to disclose this idea more than this at the moment. We have some powerful tools to do that. In fact, in the paper that I was referring, a result covers that real-time change of this W. But again, I would like to keep it simple for this lecture video. Basically, this is element-wise how we implement, And basically, agents converge for the consensus algorithm to this value. It depends on the initial conditions. It must depend on the initial condition. Um, Whatever this number is, we're gonna get more of a feeling when we do the example. Here is the example. So basically, I have 6 agents over this circle graph. And these are the dynamics that we would like to implement. This is the MATLAB code. These dynamics coming from element-wise this. For example, if you look at the first agent, W2 over W1, W2 over W1 multiplied by X1, X1 minus X2, because it changed the information with X2. Minus, it also exchanged with X6, so we have X6 here, X6 divided by X1 multiplied by x1. So I am basically implementing this equation for all the 6 agents, then running ODE45. Anyway, for these initial conditions and for these W settings, the null space 1, 2, 3, 4, 5, 6, why not? Agents converge to here. So if you calculate this value, which is the convergence value coming from theorem 2.5 of our paper, these are the numbers that you are going to get for the agents: 0.12, 24, 36. You got the pattern. You got the 1, 2, 3, 4, 5, and 6 pattern, which matches with W. And X1 goes to the lowest one because W is lowest one for it. X2 goes to its doubled number instead of 12, 24, so on and so forth. So the thing is, you can have an arbitrary initial conditions. If this agent goes to, for example, 0.5, and if your null space is like this, the second one will be 1, 1.5, 2, 2.5, and 3. It will get scaled with this W. But the main motivation why we developed this algorithm, this Laplacian null space, or the reason we ask, instead of having the vector of ones, 1, 1, 1, 1, what we can do once we have a general null space. Why we ask, why my research team asked this question was particularly for leader-follower case, because I highlighted the importance of leader-follower in the previous videos. In some of the previous lectures, they are more flexible, or we can do more on the vehicle domain for ground, aerial, underwater, water vehicles. Um, and simply, some of the agents act like leaders. We have this consensus like algorithm coming from the new Laplacian, or the new consensus algorithm per se. And we have this additional term, Ki is 1. If that agent has access to the command, then we say it is a leader agent. Otherwise, this term is not there. So theorem 3.1 of our paper says that when the command is constant, state of all agents, this is x1, x2, x3, x4, all the way up to xn, converge to that number. All right, what is this? We're gonna reveal. For now, all right, it converges to that one. That's great. Let's see if we can do more or understand more. Not do more is doing more is not the right question, but what is this is the right question. Anyway, F bar is a positive definite matrix, which is also proven in the proof of theorem 3.1. F bar is symmetric, and K is just diagonal matrix. Correspond. Let's say the first agent is the leader, second agent is the leader, all the other agents are followers. Then it is like 1, 1, 0, 0, 0 diagonal matrix K. And once such a matrix having at least one non-zero element, a diagonal element, positive non-zero diagonal element summed with this new Laplacian matrix, then the resulting F bar becomes positive definite. And when the command is time varying, this is similar to the case when I was talking about synchronization dynamics, right? When the command is slow, then you really act like, you really follow, kind of approximately follow that command. If the command is really fast time varying, then multiply the entire dynamics, scale it with some mu, 5, it is like positive constant, multiply everything on the right by 10 or 5. We did an example in one of the previous lectures. If you would like to track fast time varying comments, either use output regulation theory or multiply the right hand side by a constant. Anyway, so let's understand what this convergence means. Because whether it's a command is a constant or time varying, you directly converge there, or for the time varying case, you will converge to a neighborhood around this point. So what is this point? First of all, I would like to highlight a fact. F multiplied by W, one more time, is L bar multiplied by KW, right? I just expanded F, which is given in here. So we have L bar W plus K bar W, which is L bar W. If you remember, W is on the null space of L bar, so it is 0. So we have KW. So what we have, F bar W equals to KW. So if we take this equation, F bar is invertible, multiply both sides by F bar inverse, we are going to get W equals to F bar inverse KW. All right, sure. What this implies is that if you select command to be some gamma is a scalar constant positive multiplied by Wi. If you select command like this, there is a Wi is an element that comes from the null space. So I am selecting command as the scaled null space entry, for example, W1 multiplied by gamma. If it is confusing, think gamma as 1. Think like I am choosing command from an element from the null space. Gamma doesn't change much, just it will scale that number. Then, if you look at K1C, then K1C becomes, with the C selection, K gamma KW. You are going to have K, which will determine which W to be active. Again, if the first two agents are leaders, then 1, 1, and the rest 0 is a diagonal matrix. So these are equivalent. Instead of having K multiplied by CCC, you are going to have KW multiplied by gamma if you select C like this. So this Billy equation holds. Why do we care? Why we care? Because, now we have this limit F bar inverse K1C. So now instead of K1C, I can now write, instead of K1C, I can write gamma KW. F bar is there, KW and gamma instead of K1C. This equation is used, so we are now here. And final piece, F bar 1 inverse KW is also W. So we have limit t goes to infinity, x minus gamma W equals to 0. Meaning that if you select a command, I will illustrate this in several examples. If you select comma, for example, if your null space, let's say gamma is 1, why not? And your null space is 1, 2, 3. So you are selecting command to be 1 applied to the first agent. If you are applying command to the third agent, you can select C as a 3 because W was 1, 2, 3. Anyway, let's illustrate this. I have 6 agents over the undirected and connected graphs. First agent is the leader agent right now. This is my null space 1, 2, 3, 4, 5, 6. And I am applying a command to the first agent, which is 1, which is in its null space. Gamma is 1. I'm not scaling. I'm just taking W1, inserting it here. Now, magically, what you observe is that, yes, the first agent goes to 1, and the other agents goes to the exact null space values 2, 3, 4, 5, and 6. Convergence took a lot of seconds. So probably F bar is has an eigenvalue close to the imaginary axis. You can address this problem by choosing another leader. It can speed things up, or multiply the algorithm, as I mentioned, the right-hand side by some constant to speed this up. But when I change this leader to the number 4, it addressed the problem. So basically, if you choose it like this, again, the null space 1, 2, 3, 4, I am applying command to agent number 4 in this case. So I am inserting 4. Then it goes to 4. This purple is agent 4, but the others are going to 1, 2, 3, 4, 5, 6, exactly the null space. You must see the beauty behind this. So, if you scale, for example, if you apply 2 to the fourth agents, then everybody will go to it. It will be like 4 multiplied by 1 over 4 multiplied by 1 over 2. So gamma is like 0.5. It is like scaled. If you instead of 4, if you use 2, it will go to 0.5, 1, 1.5. This will go to 2, whatever it is applied. So they will get scaled. Now, if you do apply comments to 1 and 4, again, I am applying agent 1 to 1, the first null space entry, and the W4 to fourth agents because of their corresponding null spaces. Once again, they converge to 1, 2, 3, 4, 5, 6. Now, now I can make another example. Instead of applying 1 and 4, I am applying 2 and 8. You can think of this C1 is gamma multiplied by W1. Gamma is 2, so 2 multiplied by 1 is 2. And this one is W4 multiplied by 2. 4 multiplied by 2 is 8. So gamma equals to 2 case. You can think in terms of this. Not this one, my bad. Right, this gamma is 2. If you select C to be gamma 2 multiplied by VI, I am just illustrating this case, then agents converge to, this converges to 2, this converges to 8, the others are nicely scaled on the null space. So that's why we developed a null space algorithm. It is very flexible for especially leader follower networks. For example, let's say you have a scenario, you would like to split a multi-agent system into 3 groups. Let me show you an example. So if you do so, for example, if you would like agent 1 and 2 to remain together, then I can select my null space to be, they are the same. I want agent 1, 2 to be together. Well, 3 and 4 to be together, they should go to 2. And the last 2, they should go to 3. You can assign like 1, 1, 5, 5, 100, 100. It doesn't matter. Or you can make, you can use any positive numbers on this W. Initial condition is not important. Here I am selecting agent font to be the leader. So I'm injecting W4, which is 2, to agent 4. As you see, agent 4 and agent 3, they are going to 2, this purple and yellow colors. Uh, Last 2 agents, 5 and 6, goes to 3, and the first 2 agents go to 1. You can split the network. You basically, right, you by changing W and correctly inputting your leader follower network, you can make your multi-agent system make whatever you want to make. And if you are really deeply familiar with multi-agent systems, you may ask, well, you can say, I also see some algorithms called scaled consensus, or some algorithms that talks about kernel or null space based on similarity transformation. Well, of course, the rare, most of the literature uses a Laplacian having 1, 1, 1, 1, but there are rare, interesting works. We cited all these works in this paper, one of the best papers. I'm glad that I'm researched and co-authored and lead the development. So you can make interesting things with your Laplacian matrix. And let's go to the final example. I will go simple to illustrate this concept. And this was one of the motivating scenarios years ago, once we really at the beginning of developing this research. And the idea was, well, a bunch of agents synchronizing themselves with some value. I want one of the agents, in this case, this purple one, it is, think about the quadratic is almost out of battery. So what I want, instead of all agents go to the common point, synchronization point, one of the, or if you can make one or two of the agents, in this case, one of the agents go change the battery um, while others collaborating. As you see, it is simple. You can select for, in this case, agent 4 needs to change the battery, and we are assigning this to be the leader. So the W's are 1, 1, 1, 1, 1 for agent 1, 2, 3, 5, 6, because we want them to go to a common value. We want agent number 4 to go somewhere else, wherever that location it is right now. It is at 2. And if you run this algorithm with agent 4 being the leader, which goes to its W4, as you see, all agents go here. This purple agent goes to the battery changing location. Now, if you implement, instead of making agent number 4, you can also make agent number 3 leader. Get rid of this term here, so agent 4 is no longer leader, and inject here minus, in parentheses, x3 minus 1. W3, you need to use W3. So if you also, if you get rid of this term in here, minus x4 minus 2, and instead you make leader agent number 3 leader and inject minus in parentheses x3 minus 1, you will get the same plot. I don't know the time scale. It may be longer or shorter, but eventually at steady state, you are going to get the same plot. All right, so I hope you like this video about Laplacian null space. You can use this in your research and you can assign any vector to the Laplacian and play with it. It significantly generalizes existing consensus and synchronization dynamics. Having a null space of 1, 1, 1, 1, you can assign any positive vector to null space. And we discussed much more stuff on that paper. So I try to give you the basics such that you can look at these basics, learn. If you would like to refer, you can refer to specific theorems. I give specific theorems and remarks so that you can start using in your research. If you would like to dive more, read this paper and see you next time. Take care.